Welcome back to Discrete Mathematics. Today, we're going to take a look at subgraphs, as well as complements and other neat terminology. So, a subgraph H, which we'll call its vertex set VH and edge set EH, and that subgraph of G, which we'll call VGEG, requires two things. It requires that the vertex set of H is in the vertex set of G, which means we don't add vertices, and the edge set of H is also a subset of the edge set of G, where all of the edges in H are incident to the vertices in V. This is a bunch of jargon. Basically, what this means is if we take G, a graph, to take a subgraph, we take our vertices, and what we can do is we can either keep them all. So for instance, in a case where we keep all of our vertices, we'll call this H, we might choose to delete some edges. So for instance, this H is a subgraph of G. So H1 is a subgraph of G because we've kept all the vertices, but we're just missing a few edges. So its edge set BD, is in the edge set of G, and the vertex set ABCD is in the vertex set of G. So what's another subgraph of G? Well, there's this one, AB. This is a subgraph of G because we kept A and B, so AB is a subset of ABCD, and the edge set AB is a subset of the edge set AB, AC, AD, so on and so forth. So, that is a subgraph. What is not a subgraph is, for instance, say we have A, B, and C, and we kept all of these, and then we just have this edge sticking into the middle of nowhere. So we can't have this. This is why the edges must be incident to the vertex set, because we need a D there. In fact, another thing that's not a subset is if I said, okay, so there's A, B, C, but then we have this extra vertex, we'll put it here, called E. That is not a subset because E in our, we'll call this H4. E in V of H4 is, so this vertex E is in H4, but E is not in our regular graph G. Should say VG. So clearly not a subgraph because we added a vertex. A spanning subgraph are all the subgraphs where the vertex set is the same. So for instance, if we want a spanning subgraph of G, that means that we have to keep A, B, C, and D. Then we can do whatever we want with the edges. For instance, this graph here, H1, this is a spanning subgraph of G because we have all the vertices. We don't need to keep the edges. So that is a spanning subgraph of G. What is another spanning subgraph of G? Well, we need to have A, B, C, and D. So let's see this one, this one, this one, this one, and this one. So we're missing one edge, but it has all the vertices, so it is a spanning subgraph of G. And we'll call that H2. So that is a spanning subgraph. Again, another word you need to know. Here's a nice trickier concept. The subgraph induced by H, and we're going to show an example of this. So here's what we do. When we induce a graph, we remove an edge. So for instance, let's remove the edge C. And when we remove an edge, we just remove only the edges, crazy. We only remove the edges that were incident to that vertex. So because we removed C, we only removed CD and CA. you cannot remove any other edge. When we induce a graph, we remove only the edges incident to the vertex we removed. So for instance, if we remove E here, let's say we take E, well, then we have to remove this edge, we have to remove the edge from E to B, and we have to remove the edge from E to D. So we have to take all of these out. So H is an induced subgraph of G. So how can we write this in notation? Well, we'll get to that. But here's a question. How many spanning subgraphs are also induced? So what does that mean? How many subgraphs of G where all the vertices are kept are also induced? Well, here's an answer. 1. For every graph, there is exactly one subgraph that is spanning and induced. Why? Because spanning says all vertices. Induced says remove vertex and adjacent edges. Well, incident edges. That would be the correct term, incident edges. So, the one case where spanning is induced is when the induced says remove nothing. And that is the only scenario where the spanning subgraph is the induced subgraph. So that's a fun little question, and I put this right here just as an example. So the spanning subgraph G, well, if we remove an edge, let's say hypothetically we removed AE, it is no longer induced because we removed an edge without removing its vertex. So in an induced subgraph, you cannot just remove edges. You can only remove edges if it is touching a vertex you removed. So the graph is just a nice visual example for you to figure things out on your own if you read a slide and like, hey, I'm going to figure that out first. So maybe I tricked you. It's only one. So how do we write this? Well, if we have a graph G is equal to VE, we just write G minus the set containing whatever vertex, and this is just equal to the graph V minus that vertex with a new edge set E prime. And this E prime has all the edges incident to V removed. So for instance, if we have, say, a graph here, and this right here is our V, we have an edge, we'll call this E1, E2. So V, well, we'll call this AB. V has the edges V, A, and B, and E has the edges E1, E2, and we'll call this E3. Then V minus V, or V minus little v, is just going to be the edge set, or the vertex set AB. So we subtracted V from it. And then this E prime here is just going to be E3, because E1 was touching V and E2 was touching V. So we remove those and we just get left with A touches B through E3. So that is how we write graphs that we induce by removing specific edges. So this is an induced graph. Okay, what is a complete graph? A complete graph, which we'll always say k little n, is a loop-free undirected graph where the amount of vertices is denoted by this number n, and for all vertices that are not equal to each other, there is an edge between them. So for all a, b, and v, and a is not equal to b, the set AB is in edges. So for instance, K1, we have this vertex A, and there's an edge between all vertices. Okay, K2, we have two vertices here, and we need to connect them to each other, so that is K2. In K3, we have three vertices, and they all have to be connected to each other. So if we have 1, 2, and 3, one has to be connected to 2, and one has to be directly connected to 3. Same with 3 with 1, and 3 with 2, and 2, 1, 2, 3. Let's take a look at K4. K4. Okay, we got 4 vertices here. So this top left one has to be connected to bottom left, bottom right, top right. Bottom left has to be connected directly to all other vertices. So we can do this here, and let's loop this around. We could cross it if we want, so let's just cross it for now. And this bottom right vertex has to be connected to all others, so we'll just draw that one. So that is the complete graph K4. The reason I drew it so that way this middle was looped around is because I like it to be planar, but we'll discuss planarity a little bit later. So that's a complete graph. A complement is essentially the same vertex set. So if we have the complement, which we'll call V bar, E bar, or G bar, it means that the vertex set is essentially the vertex set of the complete graph, and the edge set is going to be all the edges in the complete graph minus the edges in the original graph G. So for instance, here's K4. It's the graph we just did on the other page. It's just shaped as a diamond. So each vertex is connected to all other vertices. And here's our graph G. So I should probably label these A, B, D, and C. So in G bar, we keep the same vertices. So we have A, B, C, and D. And what we do is we say, okay, it has all of the edges. So we should have an edge here, an edge here, an edge here, an edge here, one here, and then we'll loop this around here. But we subtract all of the edges in G. So we remove the edge between A and B. We remove the edge between, sorry, this graph was wrong. Should have looked like this. Okay, so we remove the edge between A and B, we remove the edge between A and C, and we remove the edge between A and D. So now this is the complementary graph of G. Basically, all the edges it didn't have, that it could possibly have, it now has. So here's a question. Suppose our graph, let's be a little bit more formal about this. I do remember this question from a textbook. So we have the graph G is equal to VE, and we have V. The number of edges in V is equal to little v, and the number of edges in E is equal to little e. Of course, this is going to be simple. So here's the question. What is the number of edges in E bar? Okay, well, we have G is equal to V bar, E bar. Well, really we know that V bar is the same thing as V because it has to have all the vertices still. The complement really just switches the edges from off to on and on to off. So here's the thing. How many edges are there total? So we went over this in the last video. The total possible edges in Kn, so that's going to be V choose 2. So you take all the different vertices and you say, okay, for each 2 I choose, I'm going to put an edge between them. And then we're going to subtract the number of edges in G. So this is number of edges in G. So this is how many edges there are in the complement of G. So for instance, let's take a look at this one. So we have 3 edges here. So I should probably just draw it out K4. So we'll do K4 like this. 1, 2, 3, 4, 5, 6. Okay, so K4 has 6 edges. So 4 choose 2, because we have 4 vertices and we choose 2, which is just 4 times 3 over 2, which is 6. Here is our G. So we see 3 edges here. So this means that G complement should have 6 minus 3 equals 3 edges. So that means it should have this one, it should have this one, and it should have this one, which is right. So by example, we've shown that yes, this works. And of course, you can always verify your conjectures with examples. That's a great thing to do. So that is complements. And let's do some practice. I want you to draw K5. So take a piece of paper, do it in your head, draw K5. Okay, what does K5 look like? Well, we have 5 vertices, and each one has to be connected to all the others. I'm going to do it in light green. Okay, so that goes to 4 edges, this one goes to 4 edges, this one goes to 4 edges, and that one goes to 4 vertices. In saying edges, I meant to say vertices. Okay, so each vertex goes to 4 other vertices. Got a nice, beautiful star pattern here. So, what happens when we try to make an induced subgraph? Remember what an induced subgraph is? An induced subgraph is when we take one edge, we delete it, and we delete all adjacent edges. So let's try this. Let's remove this vertex here and remove all incident edges. So this is K5 minus some vertex. What are we left with? We're left with K4, because each of these vertices are connected to 3 other vertices. Okay, so what happens if I remove another edge or another vertex? Well, then I remove, say, this one. Oh, what's that? We're now left with K3. So what happens when we have Kn and we remove a vertex? Well, if we take Kn minus some random vertex for V in the vertex set of Kn, then this is just equal to Kn minus 1. And we can keep going and going until we get back to K1. So, it's kind of interesting. In fact, when you say, okay, hold on a second, let's take a look at the number of edges here in Kn. Okay, so that's going to be n choose 2, because we have n vertices and we choose 2. So then what happens when we subtract? Okay, so that's n choose 2. Now, what do we get when we take the number of edges in Kn minus some vertex? Well, we get n choose 2, and then we subtract. Okay, so we pick a vertex, say here, and then it has to go to n minus 1 other vertices. So what happens is then we subtract n minus 1 edges. Okay, well, this is the same thing as n times n minus 1 over 2 minus n minus 1. So, well, what do we have here? We could put it all over the same common denominator. So this is going to be n times n minus 1 minus 2n plus 2 all over 2. So this will be n squared minus n minus 2n plus 2 over 2, which is the same thing as n squared minus 3n plus 2 all over 2. And you're saying, hold on a second, this has to equal n minus 1 over 2. What crazy shenanigans are you doing here? Well, let's take a look at this. So we can factor this. This will be n minus 2, n minus 1, all over 2. Oh, so now you're sort of getting it right. And this is just the same thing as basically saying n minus 2 times n minus 1 times n minus 3 factorial over 2 times n minus 3 factorial, which is really just the same thing as saying n minus 1 choose 2. So, we have proven both graphically and mathematically that the number of edges in Kn minus some vertex and all of its incident edges is equal to the number of edges in Kn minus 1. So, when you take any induced subgraph of Kn, you just get a smaller complete subgraph. So, just some simple combinatorics, and honestly, that might be pretty difficult to see. And that's totally normal, because graph theory is deceivably difficult. So, if you have any questions, as always, leave them in the comments below, or check out reddit.com/r/TrevTutor and post them there. There's more stuff at trevtutor.com, and if you can share this with your friends, that would be awesome, because you can help them, and you can help me. So, I'll see you guys next time.